theorem. Let me tell you the theorem first. The Chinese remainder theorem, simply CRT, is used to solve a set of different congruent equations with one variable but different moduli which are relatively prime. It means we are going to have a set of different congruent equations. It's clear that these congruent equations are different but with only one variable and different moduli. So we are going to find the value of this one variable using Chinese remainder theorem. I know things will be little bit not clear for you at this stage. Anyway, when we see some examples, you will understand this. Before that, let's have a theoretical understanding. So we have different congruent equations as mentioned in the definition, where x is congruent to a1 mod m1, x is congruent to a2 mod m2. We have n equations. X is congruent to an mod mn. If you see here, we have one variable which is x here, right? And we have a set of different congruent equations which is this. We have n different congruent equations. And if you note here, there are different moduli. This is mod m1, this is mod m2, this is mod mn. We have n different equations with different moduli, different a values, but the variable is 1. Now we are going to find the value of this single variable. Let's see what this Chinese remainder theorem states. So Chinese remainder theorem states that the above equations have a unique solution of the moduli are relatively prime. So m1, m2 up to mn, when they are relatively prime to each other, then there exists a unique solution x. I hope the theorem is clear for you. If not clear, no worries. Let's solve example number 1 and you will understand things clearly. Before diving into example number 1, what is the formula for finding this value of x? So the value of x can be x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse up to an mn mn inverse mod capital M. If you note here, few values are available on the question. a1, a2 up to an can be taken from the question, and we are required to calculate the other unknown variables including this mod m using the values that are available in this set of congruent equations. So this is the equation which is used to find the value of x. Let's see example number 1. Solve the following equations using Chinese remainder theorem. The equations are x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. How many equations are given in this question? 3 equations. So we are going to modify the formula in such a way that it is going to cater 3 different congruent equations. You can adjust the formula according to the need. Let's solve this now. We are going to have the equation like x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse plus a3 m3 m3 inverse whole mod m. Why we are stopping up to m3? Because we have 3 equations, 1, 2 and 3. If you have 4 equations, then add plus a4 m4 m4 inverse mod m. So it's so simple. Since we have 3 equations mentioned in the question, our formula goes like this. Now let's see what are the given data. In order to find the given data, let's see this with the comparison. We know Chinese remainder theorem, we have different congruent equations like this. X is congruent to a1 mod m1, x is congruent to a2 mod m2, and x is congruent to a3 mod m3. Since we have 3 different equations in the question, I am stopping up to this. And what's the given data in the question? It's x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Let's compare these two so that we can find the given data. So we know this is the equation we are going to apply, and the given data are a1 is 2, a2 is 3 and a3 is 2. So that's what we have mentioned here. A1 is 2, A2 is 3 and A3 is 2. Then what are all the other given data? Small m1, small m2 and small m3. So small m1 is 3, small m2 is 5 and small m3 is 7. So these are the given information. Please be noted that there exists a unique solution only when small m1, small m2 and small m3 are relatively prime. In other words, GCD of small m1, small m2 and small m3 is 1. Since there is no common factor except 1 that can divide 3, 5 and 7, we can say 3, 5 and 7 are relatively prime. Alright, when we see this equation, we can say A1, A2, A3 as given in the question, but there is no small m1 here. We have capital M1 inverse, capital M2 inverse and capital M3 inverse. In other words, these are all small m1, m2, m3, these are all big m1, m2, m3. So we are required to find capital M1, capital M2, capital M3 and capital M1 inverse, capital M2 inverse and capital M3 inverse. Also, we are required to find the value of capital M, which is this. So we will find all these values. Once all these values are known, we know A1, A2, A3 are already given in the question. We will just substitute the values and evaluate this expression so that we will get the value of X now. So let's start doing this now. So we know the given data are A1, A2, A3, small m1, small m2, small m3. Let's find capital M1, capital M2, capital M3 and their corresponding inverse, also capital M. To find capital M, it's so simple, it's the product of all these small m's. So we have small m1, small m2, small m3, right? So capital M is the product of small m1, small m2 and small m3. So when we substitute this, we get capital M is equal to 3 into 5 into 7, which is equal to 105. So we found the value of capital M, which is 105 here. We are done with finding capital M. Let's now move on to find capital M1, capital M2 and capital M3. So let's navigate to finding capital M1, capital M2 and capital M3. How to deal with this? So we are going to find three values, capital M1, capital M2 and capital M3. So the formula is capital M1 is equal to capital M upon small m1. That is what we have found here, capital M upon small m1. Similarly, capital M2 is equal to capital M upon small m2 and capital M3 is equal to capital M upon small m3. We know the values of capital M and all small m values, right? We will just substitute it here. So when we simplify this, we get capital M1 as 35 and capital M2 as 21. Why 21? Because capital M is 105 and small m2 is 5, which is this. So we get capital M2 as 21 and capital M3 as 105 upon 7. Why 7? Because small m3 is 7. So when we substitute this value, we get capital M3 is equal to 15. Now we have found out the values of capital M1, capital M2 and capital M3, which is 35, 21 and 15 respectively. So we have done finding most of the values. So now we are required to find capital M1 inverse, capital M2 inverse and capital M3 inverse. The formula for finding capital M1 inverse, capital M2 inverse and capital M3 inverse are projected here. It's so simple. We know capital M1, right? So we are going to find the multiplicative inverse of this capital M1. So when capital M1, when it is multiplied by its multiplicative inverse, we should get remainder 1 when we perform with mod small m1. Please focus on this row. So when this value is multiplied by its inverse, we will get 1 as the remainder under mod m1. Similarly, capital M2 is multiplied by capital M2 inverse will give 1 under mod small m2. Similarly, capital M3 is multiplied by capital M3 inverse will give 1 under mod m3, which is small m3, which is this. So we will substitute the values what we have found. So let's focus on finding capital M1 inverse. So we substitute M1 to be 35 because that's what we have found it in the previous step. So we have 35 is multiplied by capital M1 inverse will give 1 mod 3. Why 1 mod 3? Because small m1 is 3. Now you can go for extended Euclidean algorithm to find the multiplicative inverse, or you can start applying from the values 1, 2, 3 till you get the final result. So let's start with 1. When capital M1 inverse is 1, 35 into 1 is 35. Then 35 when it is divided by 3, are you getting 1 as the remainder? 35 when it is divided by 3, you get 2 as the remainder. So M1 inverse is not 1. Let's try 2. So 35 into 2 is 70. 70 when it is divided by 3, we get 1 as the remainder. So we have M1 inverse as 2. We easily found it out because all these values are small numbers. So I am not going for extended Euclidean algorithm for solving this. If the numbers are big, I want you to find the multiplicative inverse using extended Euclidean algorithm. If you are not sure about this extended Euclidean algorithm for finding the multiplicative inverse, I request you to watch my previous lectures. We are done with finding capital M1 inverse. Let's now move on to capital M2 inverse. So we know capital M2 is multiplied by capital M2 inverse will give 1 mod small m2. So we will substitute the values here. Now let's start applying 1 to capital M2 inverse. If we use M2 inverse as 1, 21 into 1 is 21. 21, when it is divided by 5, we get 1 as the remainder. Yes, it's perfect. So we know capital M2 inverse is 1. And we will move on to the next step, finding capital M3 inverse. We will apply the value capital M3 is equal to 15, which is this. Now 15 is multiplied by what? We will get 1 as the remainder when it is divided by 7. Let's apply 1. So 15 when it is divided by 7, we get 1 as the remainder. So M3 inverse is also 1 in this case. So we have found out the values of capital M1 inverse, capital M2 inverse and capital M3 inverse. We will substitute the values. So now we got all the values that are required to find the value of x. Alright, we know how to find the value of x, which is this. So it's clear that we have all values that are required to be placed here so that we can evaluate this expression and find the value of x. Let's solve it now. So the given question is here and we are going to solve. X is equal to A1 capital M1 inverse plus A2 capital M2 inverse plus A3 capital M3 inverse the whole mod M. I'll bring the table from the previous slide. So this is the value. I'm gonna take this and place it here. Alright, now let's substitute the values here. So we get this expression. Just fill these values from this table. Now when you evaluate this, you get 233 mod 105. Why 105? Because capital M, which is 105 here. So when you evaluate this, you get 23 as the remainder. So finally, we got the value of x to be 23. So we found out 23 is congruent to 2 mod 3, 23 is congruent to 3 mod 5, 23 is congruent to 2 mod 7. Is this correct? Let's verify this. Let's take the first equation. 23 is congruent to 2 mod 3. 23 when it is divided by 3, are you getting 2 as the remainder? 3 7 times 21, we get 2 as the remainder. It's matching. Perfect. Let's move on to the second equation. 23 is congruent to 3 mod 5. So 23 when it is divided by 5, are you getting 3? Yes, 5 4 times 20, remainder is 3. So this is also perfectly fine. Let's move on to the third equation. 23 is congruent to 2 mod 7. 23 when it is divided by 7, 7 3 times 21 and the remainder is 2. Perfect. So we found out the value, that is the single variable x, to be 23, and we also have verified the result. So Chinese remainder theorem is helping us to solve the different congruent equations under one variable. Please be noted that only one condition. The condition is these moduli values should be relatively prime. Only then we will get the correct result. I hope things are clear to you.